Hello everyone, my name is Dakota Fulp, and today I will be presenting our automated approach to resiliency for lossy compressed data using error-correcting codes. To begin, I will first discuss the motivation behind this work and some necessary background information. Following this, I will detail the findings of our soft error fault injection study on lossy compressed data. Finally, using this information, we develop ARC, or the automated resiliency for compression. Now, high-performance computing has advanced quickly over the years and has revolutionized the way researchers solve problems. These advancements make previously intractable problems possible and enables better application performance. For instance, using HPC systems, the Hurricane Isabel, CESM, and the NICS simulations were made possible. However, as these simulations become more powerful, they are also producing vast amounts of data which cause significant bottlenecks in the I/O subsystem. To resolve this I/O bottleneck, researchers often use different forms of compression to reduce the resulting HPC datasets. One common approach to compression is through lossless compressors such as gzip or zstd, which reduce data size with no loss in precision. However, due to the high entropy of the mantis bits in HPC floating point data, they suffer from suboptimal compression ratios when used on this type of data. To resolve this issue and achieve higher compression ratios, lossy compressors such as SZ and ZFP reduce data precision during the compression process while abiding by a user-set error bound. This approach makes them ideal for HPC floating point data, as full data precision is not always needed. Now, SZ uses a block-wise prediction-based compression model, and in this work, we examine three of its error bounding modes. First, the absolute error bounding mode ensures each data value uses the same user-specified error bound, which ensures uniform precision for all values. As seen here, D and D prime are the original and decompressed values, while epsilon is the error bound the user chose. Second, the point-wise relative error bounding mode uses the product of a data value and the set error bound to determine each data value's specific error bound. And finally, the peak signal-to-noise ratio, or PSNR mode, compresses the data to retain a minimum PSNR rating. PSNR is a metric often used to assess data distortion levels when using lossy compression, and this mode focuses on overall data integrity rather than any individual data value's quality. ZFP uses a blockwise transformation-based compression model, and in this work we examine two of its error bounding modes. First, the fixed accuracy mode works in a similar fashion as SZ's absolute error bounding mode and ensures each data value uses the same specified error bound. Second, the fixed rate mode divides the data into 4 to the d size blocks, where d is the data dimensionality. The product of the user-defined rate and 4 to the d determines each block's compressed size. This means a lower rate leads to a higher compression ratio and less precision in the data. For example, seen here, given a 1D double array, each block of data would comprise 4 doubles, and given a rate of 48, ZFP would compress each of these blocks to 192 bits, but given a rate of 16, it would compress each block to 64 bits. Now, while SZ and ZFP are both effective lossy compression frameworks, there has been little work that investigates how lossy compressed data reacts to soft errors. And as soft errors are a common threat on HPC systems, resiliency to such soft errors is critical for all HPC applications and data. Here, we see the effects of 2 single-bit soft errors into the compressed Hurricane Isabel dataset. And while each of these errors occur at a different bit location in the compressed data, in both cases, large portions of the data become unusable and highlights the sensitivity to soft errors that lossy compressed data has. To better understand this sensitivity to soft errors, we conduct an extensive fault injection study. In each experiment trial, we flip a single bit of the compressed dataset that is stored in application memory. We use a 1%, 0.1%, and 0.01% uniform sampling of CESM, Hurricane Isabel, and NICS to determine which bits to target. After flipping a bit, we attempt to decompress the data and record the return status. If decompression is successful, we record the percent of elements whose error violate the error bound, the maximum absolute difference between the original and decompressed data, and the PSNR rating of the decompressed data. Upon finishing all trials, we start by examining the return statuses and group them into 4 categories. The completed trials mean the data decompressed with the error present. The compressor exception trials mean the compressors caught the error and threw an exception. The terminated trials mean the application crashed during decompression. And the timeout trials mean the decompression process took 3 times the average time trying to decompress. Here we show the results for all trials. On average, we find 95.28% of all trials completed, while the other 4.72% of trials fell into the other 3 categories. These results are similar to the results found by Avermenko et al. When they studied lossless compression. Overall, we find these results troubling as completed trials do not acknowledge soft errors and have a high probability of error propagation and silent data corruption. Even more troubling, we find 100% of all trials using ZFP completed, which indicates ZFP will never inherently catch soft error data corruption. From this, we conclude that if soft errors impact lossy or lossless compressed data, silent data corruption is likely. Next, we examine the error's impact on the error bounding of compressors by focusing on the completed trials. Using our results, we calculate and show the percent of decompressed values whose error violate the set error bound. For the SCABS, SCPWREL, and ZFP ACC results, we find a single soft error in the compressed data leads to, on average, 10% of incorrect elements. Specifically, for SC-ABS, this ranges from 0.01% to 80%. For SZ-PWREL, this ranges from 0.03% to 64.4%. And for ZFP ACC, this ranges from 0.002% to 53.6% incorrect. This demonstrates that certain bits are more important than others in the decompression process. However, unlike the other three modes, ZFP rate mode only had an average of 3.5 data values whose error violate the error bound after a soft error occurs. This is due to the block-based compression model it uses, which prevents the error from propagating, but also limits the compression ratio to 4x, while the other three achieve compression ratios of 500x, 45x, and 17x respectively. To fully understand soft error effects at different compression levels, we alter each mode's error bound to achieve compression ratios of 50x, 25x, 13x, and 7x. Upon reviewing each row, we find higher compression ratios, which require less strict error bounds to achieve, mask small soft errors in the data. However, to achieve compression ratios of 50x or 25x with ZFP ACC, for example, we must use error bounds of 10 and 0.5, which introduce too much data distortion to be realistically used. Therefore, even though less strict error bounds mask the error, they are not suitable for scientific data in most cases. This data also reveals artifacts of the compression process, with all graphs exhibiting a downward slope at lower compression ratios. For SZ, this shows its final lossless compression pass, and for ZFP, this shows the effects of its data value grouping and encoding steps. Lastly, we quantify the drop in data integrity due to a soft error, and do so by recording the decompression bandwidth, maximum difference, and PSNR. When looking at the decompression bandwidth, we find the control and corrupt results to be relatively similar, with large differences occurring in the standard deviation. In rare instances, we also find very high or low bandwidths, which are caused by corruptions in the stored metadata that control the decompression process. Therefore, in some cases, if decompression completes outlandishly fast or takes too long, this could be an indicator of corruption. When looking at the maximum difference, we find that the difference greatly exceeds the control case in all trials and is only order of 10 to the 19 or to 10 to the 38. This order of magnitude shift is due to errors in bits used to rebuild the more significant bits of data values, but by looking at the standard deviation, we see this is not always the case. When looking at the PSNR, we find the corrupt trials have a significant shift in PSNR, with the only exception being ZFP rate mode, which contains the error to a single block. Looking at the variance, we find the PSNR is not easily predicted and fluctuates depending on the error location. Overall, we find data compressed using either SZ or ZFP does not exhibit a natural resiliency to soft errors, and while ZFP rate mode does demonstrate some resiliency, is incapable of achieving high compression ratios in its current state. In our research, we aim to resolve this sensitivity through a black box approach that will work for all compressed data. This approach must ensure no errors are present before decompression occurs, and must provide equal protection to all bits, as it is difficult to determine the most sensitive in a black box way. Now, current techniques to protect data include data duplication, algorithmic-based fault tolerance, and error-correcting codes. Error-correcting codes allow for detection and correction of one or more errors by adding redundant bits to the data. When designing our tool to protect lossy compressed data, we chose to use error-correcting codes as they are application and data agnostic and require significantly less space compared to keeping multiple copies of a dataset. In this work, we use 4 different ECC approaches. Single-bit parity can detect all single-bit errors and odd multi-bit errors, while introducing minimal overhead. However, it cannot correct any errors or detect even multi-bit errors. Hamming codes can detect and correct single-bit errors. Sectite codes work in a similar fashion to Hamming but can also detect double-bit errors. And finally, Reed-Solomon codes work by breaking the data into blocks called data devices before using them to construct code devices. Following this, they can correct devices up to the number of produced code devices. And while this makes them robust, they do introduce high amounts of overhead. Now, while error-correcting codes are a valuable tool to protecting lossy compressed data, choosing the correct one and the correct parameters is difficult without an in-depth knowledge of each. To resolve this issue, we develop ARC, or the Automated Resiliency for Compression. Here we show an overview of ARC's internal process. To begin, ARC requires the input data be in the form of a byte array, which enables ARC to protect lossy, lossless, and similar style data. Given this data, ARC must then be initialized before the user can encode the data. When calling the encode function, ARC also requires user constraints on storage, overhead, desired throughput, and resiliency. And using these constraints, ARC determines the optimal ECC configuration and encodes the data before returning it. To decode the data, users must call the decode function. Once called, ARC determines the correct ECC decoding method and checks the data for errors. If errors occur, ARC fixes them if possible and returns the data. If the errors are not correctable, ARC raises an error to the user. Once the data has been decoded, the user must then decompress the data using their corresponding compression scheme. The primary point of contact users have with ARC is through the ARC interface. To begin using ARC, users must call its initialization function and provide a maximum number of OpenMP threads available to ARC. To achieve user-desired throughputs, ARC uses OpenMP to boost ECC throughputs, and by allowing the users to set the maximum number of threads, this ensures ARC remains lightweight and does not take too many resources from the host application. During the initialization phase, ARC checks for previously cached configurations and loads them if possible. If this is the first time ARC is run on a system, or if some configuration data is missing, ARC trains all ECC configurations on the necessary number of threads and saves the data. As we show here, the total training time depends on the maximum number of threads, but only increases logarithmically and represents only a small portion of ARC's total uptime. Now, once initialized, users can call ARC's encode and decode functions. When encoding data, ARC requires a memory, throughput, and resiliency constraint. The memory constraint acts as an upper bound on the storage ARC should use when encoding the data and is defined as a fraction of the byte array size the user wants to add as protection. For instance, providing a memory constraint of 0.25 ensures the resulting data size is not more than 25% larger than the original byte array size. However, the user can provide ARC any size to disable the storage restriction. The throughput constraint acts as a lower bound for the encoding throughput and is defined in megabytes per second. For instance, if the user provides a throughput of 200 megabytes per second, ARC uses the correct ECC configuration and number of OpenMP threads to achieve this throughput. However, the user can provide ARC any BW to disable this throughput restriction. Finally, the resiliency constraint acts as a filter by limiting the potential ECC methods available to ARC to only those defined by the user. This constraint takes an array of any combination of ECC method flags such as ARC-RS for read-Solomon encoding, error response flags such as ARC core sparse, which ensures ECC methods that can correct sparsely populated errors, or the number of expected uniformly distributed soft errors per megabyte of data. However, the user can also provide ARC any ECC to allow all ECC configurations. As we have shown here, integrating ARC only requires 4 lines of code. However, ARC also allows users to interact directly with the internal functions and add new constraints and ECC methods through the ARC engine backend. This direct communication and manipulation of the backend enables users to have full control over all encoding and decoding, while also enabling developers to seamlessly integrate ARC into their applications. With ARC designed, we move to evaluate its scalability, performance, resiliency, and ease of use. As ARC intends to solve HPC system soft error issues, we begin by evaluating the scalability of its ECC approaches. When evaluating how these algorithms scale, we run on an Intel Xeon Gold 20-core, 2-way hyper-threaded CPU with 372 GB of memory and set the maximum number of threads for ARC to 40. We run 10 trials using the CESM dataset for each ECC approach and thread count, and plot the averages and variances for the encoding and decoding processes here. From these results, we find the throughput of all methods ranges from 0.04 to 3,730 megabytes per second. Specifically, when checking the 40-to-1 thread speedup, we find parity, Hamming, Sected, and read-Solomon demonstrate speedups of 19.7x, 26.8x, 33.9x, and 16.4x respectively. We find similar results for the decoding process, with all methods ranging from 10.64 to 3,602 megabytes per second. When looking again at the 40-to-1 thread speedup, we find parity, Hamming, Sected, and read-Solomon demonstrate speedups of 18.6x, 33.5x, 33.5x, and 18.3x respectively. These results demonstrate a wide range of throughputs are available to ARC and show it is more than capable of keeping pace with the less than 200 megabytes per second throughputs as Z and ZFP demonstrate. However, as soft errors require more computation during the decoding process, we must also ensure the decoding scalability when soft errors are present. To evaluate how soft errors affect the decoding process, we perform 2 experiments. First, we inject a single correctable soft error into the encoded blocks of data. Second, we inject 100,000 random correctable errors into the encoded blocks of data. Each injection is done while ensuring the error is correctable, as we wish to evaluate the correction process. When looking at a single correctable error, the only ECC algorithm, throughput, that changes is read-Solomon due to its high repair cost. This drops the 40-to-1 thread speedup from 18.3x to 2.7x. When looking at the worst case scenario of 100,000 correctable soft errors, we can see significant drops in the throughput of all 3 methods. Specifically, the 40-thread speedup of standard Hamming, Sected, and read-Solomon drops to 2.64x, 2.43x, and 1.1x respectively. However, even with these large drops, all 3 maintain a workable throughput above 7 megabytes per second and correct the data. Therefore, it would take more correctable soft errors than would likely occur to reduce the decoding throughput to such low levels. But in the more likely case of a single correctable soft error, ARC's decoding process continues to demonstrate high throughputs. As every user's needs are unique, one of the main goals of developing ARC is to satisfy user needs efficiently. With this in mind, we evaluate ARC's ability to satisfy user constraints on storage and throughput with any ECC and limited ECC options. When evaluating ARC here, we use the CESM dataset, SCABS, and an error bound of 0.1. We also set the maximum number of threads to 40 and use the same system as our scalability evaluation. When evaluating ARC's abilities with any ECC method available, we find ARC meets user demands efficiently. For instance, when given only a memory constraint as seen in the left graph, we see ARC uses all of the allotted space to provide the highest level of protection. Similarly, when given only a throughput constraint, as seen in the right graph, we see ARC uses the strongest ECC method that can still achieve the desired throughput. However, when we limit ARC to any single ECC method, ARC cannot use all of the available storage or meet the user's defined throughput in all cases, and this is due to the limitations of the chosen ECC method. For instance, when using only single-bit parity, ARC applies parity at a byte level and as such develops a stepwise function and cannot always use all the spaces allotted. Similarly, when using only SecDeb, ARC uses enough OpenMP threads to achieve the desired throughput, but as the SecDeb algorithm has a limit on speedup, it cannot always achieve the desired throughput and instead achieves as close as possible to it. Now, in the case where a user provides all three constraints to ARC, ARC works to meet the requirements of all constraints as best as possible. In this case, ARC begins by using the resiliency constraint to filter the potential ECC configurations. Following this, ARC then uses the memory and throughput constraints to create two lists of potential configurations that satisfy each constraint individually. Lastly, ARC compares both lists to find a configuration that satisfies both the memory and throughput constraints. In the event this is not possible, ARC scans both subsets for the configuration that best satisfies both. In this case, the configuration may not use all available space or meet the desired throughput requirements, but instead will provide the configuration that best meets the user requirements. Overall, from this performance evaluation, we find ARC works best to meet all user demands, even when these demands may not be possible for it to achieve. Finally, to demonstrate ARC's resiliency and ease of use, we describe how ARC could be used on two recently decommissioned production-level HPC systems, Hopper and Cielo. We choose to use these two systems as Sid Rahani et al. Analyzed the failure rate per DRAM device over 30 days for each system. Using the information from their study, we calculate a failure due to a soft error would occur every 5.43 days on Hopper and every 1.9 days on Cielo. Of these failures, we calculate that on Hopper, 94.6% are due to a single-bit soft error, and on Cielo, 70.79% are due to a single-bit soft error. Of the multi-bit errors present, we find only 4% are burst errors on Hopper, while the majority are burst errors on Cielo. With this information in mind, applications running on Cielo require ECC methods that can handle burst errors, such as read solemn. To accomplish this with ARC, the user can specify ARC-RS or ARC-core burst in the resiliency constraint. Conversely, Hopper does not require as robust of an ECC method, and instead users can specify ARC-SecDed or ARC-core sparse to ensure their data is protected. Overall, if the user understands the type of soft errors they may encounter on a system, ARC is more than capable of providing adequate protection from these errors. And as we mentioned earlier, this change only requires 4 lines of code to the actual host application. In conclusion, our research shows SZ and ZFP do not exhibit natural resiliency to soft errors and require some type of protection to ensure data integrity. Specifically, our findings show 95% of soft errors go unnoticed during the decompression process and lead to an average of 10% of data values being incorrect. To resolve the sensitivity seen with lossy and lossless compression, we develop ARC. ARC is capable of resolving these issues while abiding by user constraints on storage, throughput, and resiliency. We have also shown that ARC scales with more resources, accurately meets user demands, and is simple to implement. By using ARC, users can easily protect their data from these types of errors. In future work, we plan to add additional ECC algorithms and improve existing algorithms, use other parallelization paradigms, and implement an API to further simplify the addition of custom ECC methods and constraints. Thank you for your time, and at this moment we will take any questions.